Assalamualaikum. Welcome to our new topic, torsion loading. This is chapter number 5 from the book we are being studying. In this chapter, we will study about another type of load which mainly depend upon torque. Here are some basic concepts regarding this chapter, like what is torque, what is torsion, what is torsional load, what is shaft, and a simple twisting due to torsional loading in the diagram is being shown. Basically, torque is used to transfer the turning effect of the force from one point to another, and mostly it is in the term of power transmission. In this diagram, uh, segment of turbine is shown to you, in which turbine is transferring the power to a motor or to generator to generate some electricity. The shaft AB is marked in this diagram. Now in this diagram you can observe that there is an electromagnetic force of the motor, and then it is to flange to couple. The couple may be to some generator to generate electricity or something else. It depends. But simple concept is that to show you the simple shaft is used to transfer the power or transfer the turning from one point to another. Some other options are gears are also the part, but in this chapter we will focus on torques only. We will start about our discussion from the resisting torque. Torque you already know, but what is resisting torque? Is the torque developed inside the shaft due to applied torque. And this topic is important while we are proving the torsional formula. Already we have shown the motor and the shaft setup, in which torque T is applied on the left, and resisting torque in the shaft is produced on the right side. This is the diagram of the segment we have already shown to you. The cross-sectional view is being shown in the form of circle. Here you can consider a small area dA, which is at rho distance from the center. This area is so small that on that segment the shear stress produced in that shaft will remain the same. Basically, shear stress is varying on each and every point, but this area, although it is shown very big to you, but this area is very small, and over that area shear stress is assumed to be constant. Because we are studying the torsional loading, in this type of loading only shear stress and strain are important. As we have already studied the axial loading, in axial loading normal stress and normal strain are important. Here shear stress and shear strain are important, and also modulus of rigidity is important. So our discussion will only on shearing stress, shearing strain, etc. So this is a segment. Now, if we want to convert the force or find the force acting on that specific segment, we know that force is stress into area. The stress is tau and the area is dA, as shown in the figure. And we know that what is the torque? Torque is force and to distance, perpendicular distance from the point of rotation to the point where force is applied. Here the force is tau dA and the distance is indicated by rho. You can observe the resisting torque as a whole. We will integrate this over the area and we will have resisting torque, which will be equal to the torque applied. Before we move ahead, we have to make some important assumption while discussing the concept of torque. Here is a shaft shown to you. There are some segments are marked on the shaft. These segments are, you can observe, they are plane. You can see that the small segment on the shaft before applying the torque. What happened when we applied the torque? The B point, it moved to the point B dash. For this assumption, we have assumed that the one end of the shaft is fixed and the other end is free. you have performed this type of tests while operating the torsional testing machine, in which one end of the shaft was fixed and other end you are applying some known torque. So this is the torque applied, and what happened, the segment deformed like this, but still this is segment is remain the plane, the area of the segment remain the same, only the shape little bit move, the point E to move to E dash and D to D dash. But you can observe that theoretically the movement of point E to E dash is same as the point D move to D dash. This is our assumption. And this movement angle, the angle EFE dash, is called shear strain. So what we conclude, the plane segment remain plane. Before moving forward, normally you observe that the mostly shafts used for power transmission and for other purpose, they are round, not square. What are the reason? The square rod, they are axis symmetric. Why they are axis symmetric? In our last slide, we have discussed that the plane segments after applying the load remain the plane, but in case of square shafts, this not happen. The Due to twisting, they did not remain planes, but they move in other axes. You have seen. That's why normally square rods are not used for our set purpose. So we will move further for the proof of torsional formula. The torsional formula have different segment. Like first segment we have discussed about the resisting torque. The second segment is torsional shearing strain. You observe that shaft is fixed from one end A and from B end it is free, and the length of the shaft is L, which is equal to AB. So when we applied some torque, the B point moved to another point B dash, and this theta, from at which the angle it is moved from with respect to center B O B dash, where O is the center of the shaft. This is angle is called angle of twist. We will discuss this later. And the angle BAB dash, it is the same angle we have already discussed about the deformation of segment in previous slide, and now this is called gamma C, which is the maximum strain developed on the surface of the shaft. Why it is maximum? Because if you observe that in the center there is no strain, so when we move away from the center toward the surface, the strain will increase, and at the surface there is maximum strain, known in this chapter, in this discussion we will call it gamma C. So before moving further, we have to declare some terminology, like tau is shear stress at any point which is distance rho away from the center of the shaft, and gamma is shear strain at any point which is rho distance away. G is the modulus of rigidity, a material property, very important aspect. Tau is the maximum shear stress. Obviously this stress will be produced at the surface of the shaft. Gamma C is the maximum shear strain produced on the surface of the shaft. Rho, it is not P, it is rho. It is an arbitrary distance from the center of the shaft to the point under consideration. C, here we will term that radius of the shaft. Due to this C, we call it tau C, the maximum shear stress, and gamma C, the maximum shear strain. L is the length of the shaft, and theta is already introduced as angle of the twist. The same shaft we have discussed earlier, we have another diagram of that the shaft. One end is the fixed and another end is the free, where we apply some torque. The length of the shaft is AB, as shown on this line AB, and the center is O. The B point connect with the center with line OB. This is the radius of the shaft OB. And when we apply some torque T, the B point move to B dash, as it is free and NA is fixed. It moved an angle called theta, which is angle of twist, and when we connect the line A to B dash point, it make an angle which is shear strain and maximum shear state, it is called gamma C. Arbitrarily we observe a point D between O and B, and rho is the distance OD. This point also move to D dash when we apply the torque, and when we connect the D dash with line A, it make an angle gamma. So now you can observe that OBB dash is a sector, and in the sector we have the formula L is equal to R theta, where L is the length of the arc. In this case the length of the arc is BB dash, radius is C, and theta is the angle. For this purpose theta should be in radian because it is a requirement of the formula. If theta is in radian, length of arc BB dash and radius will be in the same unit, maybe meter, maybe feet, maybe inches. So in the other sector ODD dash, the dd dash will be equal to rho theta by following the same formula. If we have a front view of the shaft, we have one line A and B. You can observe that the B and D, even point O, they fall in the same line, but O here we are not going to consider. But from the front, B and D point will be at same location. So when we apply torque, what happened? B move to B dash and form an angle which is basically representing the shear strain gamma C, and D move to another point D dash representing an angle gamma which is also shear strain. From this view you have a clear understanding that B dash and D dash, they are different. So if we observe the triangle ABB dash, tan gamma C will be equal to BB dash over AB, because BB dash is the perpendicular and AB is the base. PB dash over L because AB is equal to L. Basically we are talking about the metals, and for such metals this deformation is very small, and we know that for very small angles taken in radians, tan gamma C is equal to gamma C. I'm talking about radians, I'm not talking about degree. So gamma C is here in radian. So by applying this option we can say that gamma C will be equal to BB dash over L, and from our sector approach we know that BB dash is equal to C theta. So we have a relationship for gamma C is equal to C theta over L. In the same way, if we go to the triangle ADD dash, we have gamma is equal to rho theta over L. So the equation for gamma C and gamma can be rewritten as theta is equal to gamma C into L oblique C, and gamma can be rewritten as theta is equal to gamma L over rho. So both are the same angle of twist, we can compare them, and by comparison you will see that gamma C L over C is equal to gamma L over rho. Here L is common, it will be cancelled out. We have relationship is that gamma is equal to gamma C into rho over C. This is very important relationship. In this relationship, for specific shaft, C is constant because it is a radius. Gamma C is also constant because the maximum possible shear stress on the surface. So rho and gamma, they are variable. Gamma is the distance from the center. So as well as rho is the distance from the center to the surface. So as the value of rho increase, strain will be increased, and when the rho is equal to C, gamma will become gamma C. We will move toward other segment of torsional formula. It is about torsional shearing stress. We know that in shearing stress G is equal to tau over gamma, and it can be written as gamma is equal to tau over G. And similarly, G is the ratio between stress and strain. So if we are talking about maximum stress like tau C, then it will be between tau C and gamma C, where gamma C is the maximum strain. So from here we can say that gamma C is equal to tau C over G. We have already proved that gamma is equal to gamma c into rho over c. Replacing the value of gamma in gamma c, we have this equation tau over g is equal to tau c over g into p over c. Or we can rewrite this equation, and final equation we will have tau over rho is equal to tau c over c. Now this relationship represents the shearing stress, the relationship between the maximum and shearing stress and the shearing stress at any point distance rho from the center. We also know that resisting torque or torque was the integral A into tau dA into rho. So keeping in view this, we can place the value of tau from the as we have already calculated, and the final equation we will have tau c over c integral a rho square dA. As I have already told you that tau c and c, they are constant, so they can be taken out of integration sign. The term integration with respect to a rho square dA is called polar moment of inertia, which is the cross-sectional resistance to the torsion, and it is a shape factor. This J is very important. It will tell us if we have same weight of the shaft, same material of the shaft, but if the shaft is circular, shaft is hollow circular, shaft is square, shaft is of triangle shape, in all these things the shape is important when it rotates, and the rotational effect will be count down with the help of J. So this formula will be compiled as T is equal to J into tau C over C, or we have already know that tau C over C is equal to tau over rho. So the formula can be written as T is equal to J tau over rho, where J is the polar moment shape factor, tau is the shearing stress at any point rho distance away, and T is the total torque transfer. Shear stress and polar moment of inertia, we will discuss about what is the effect of the shape on J and shear stress. If we have some solid shaft, the value of J will be pi by 2 r raised to power 4, and if we have some hollow shaft, obviously hollow shaft have two radius, outer radius and inner radius, the formula will be changed. And what would be the stress distribution? You can observe that the stress distribution, it is 0 at the center and maximum on the surface. And in case of hollow shaft, because in the center there is nothing, so the distribution of stress is only in the solid portion of hollow shaft. There is no material in the center. It makes the uh, shaft lighter, and it can save the material, and it can make it efficient. The next step of torsional formula is torsional displacement. It is also known as angle of twist. We have already these equations, already we have proved this equation in different slides, and these are different some arrangement of the equations, like how we can write tau is equal to T over rho into J, or it can be rewritten as tau over rho is equal to T over J. So keeping in view these equations, T over J is equal to tau over P, as well as T over J is also equal to tau over P is also equal to G theta over L. So tau over P have two relationship. One is with respect to G theta over L, and other is with respect to torque over J. So these are the two different relationships, but they can be combined, and these three terms combine to form as torsional formula. These formula is very important, and from this relationship G theta over is equal to T over J, we can write as theta is equal to TLJG. Angle of twist is very important. Why it is important? That when we apply torque and it produce some angle of twist, and every material have some ability, and if angle of twist increases from that ability, the shaft will break. So we have to calculate that in this equation. You can observe that we have the torque, which we have to transfer. We have the length, which is the design requirement, how long the shaft should be. We know the shape G. We know the material by G. The J is shape factor. G is the regarding material, made of aluminium, it is made of steel, it is made of mild steel, low carbon steel. Everyone will have some different value of G. All these will give us about for specific torque, for specific length, for specific shape, for specific material, they will give us some unique value of angle of twist, and we will go through the material properties and we will see if this angle of twist is acceptable for that material or not. Otherwise, we have to change our design by changing the torque, by changing the length, by changing the shape, by changing the material. On the other hand, if we have some material limitation that let's say it can produce only 1 degree angle of twist, the material is made of steel, will have some fixed value of G, and the material is of circular shape, we have value fixed of J, and we know that it is specific length like 1 meter. Then we will have torque. This is the maximum torque the material can transfer. So these relationships are helpful for designing that how much torque we have transfer or how much torque we can transfer by using some specific material of specific length and shape. On the other hand, this torque is also written in this form, where is J tau over rho from the previous equations, or it can also be written as J tau C over C. Now it is another way to find out the torque. Let's say if we know the shape of the shaft, we know how much maximum shear stress it can bear, and if we know the size of the shaft, when we talk about the size means the diameter. So C is basically half of the diameter because C is the radius. So this is another way to assess that how much torque a specific shaft can transfer. These two equations are different. In one equation we consider the material type like steel and other thing and angle of twist. In other we consider the maximum allowable shear stress the metal can bear. So while designing we use both of these equations, and then we can finalize how much torque the material can transfer. This some other description you can go through yourself. This is example 5.1, very important but simple. In this there is a shaft is shown at end A, there is unknown torque. At joint B, there is torque different applied about 20 feet K, where K means kilo pounds, and at C opposite torque is applied of 5 feet K. The segment AB is 9 feet long and 6 inch in diameter, where segment BC is 4 inch in diameter and 5 feet long. We have to find three things: maximum shearing stress in the shaft, the angle of twist of end B of the segment 6 inch with respect to A, and the angle of twist of C with respect to A. For part A, maybe we can assume that AB have some maximum torque and there will be maximum shear stress in AB, and AB is bigger in diameter, so maybe AB has. We cannot say at this point until unless we can perform calculation. We will discuss it in the next slide. So first of all, we have to find the maximum shearing stress, and we have to find some unknown shearing stress, which is T6, or also called TA, and T4, which is also called TB. This is the first diagram showing the T6. Now if we look at this diagram, the sum of moment should be equal to 0, because it is given condition that a movement or torque equilibrium is under this equilibrium condition due to torque. So if we have T6 as counterclockwise taken as positive, then there is two other torque 20 and 5. So the T6 is the resultant torque due to 20 and 5. 20 and 5, they are in opposite direction. So 20 minus 5, 15 feet kilo pounds, or 15,000 into 12 inch pound. This is the torque in that start from point A and till point B, this torque remain constant. It is the same as we have studied in our last chapter, that the force diagram, from one end the force is applied and until the next force is applied, the force in that segment remain the same. On the same way, we draw this diagram to find T4. In this segment only one torque of 5 is applied, so we can find the T4. If we draw the torque diagram, and T6 is counterclockwise, which is taken in the downward direction. It is our basically assumption, we draw it in the downward direction, doesn't matter. So from point A, there is a torque of 15 foot K is applied. This torque we have calculated ourselves, and this torque go move up to point B, where an opposite torque of 20 is applied. So 15 was counterclockwise, 20 was clockwise, the resultant will be 5 clockwise. And this is the same as T4 we have already calculated. And from point B to C, there is no other torque is applied. At C point, again the 5 torque was applied in counterclockwise direction, whereas T4 was 5 in clockwise direction, and resultant torque becomes 0. So this diagram tells us that from segment A to B there is 15 feet K torque in clockwise counterclockwise direction, and from B to C there is a torque of 5 in clockwise direction. This direction is very important for us. Now we apply the formula. We know that tau max is equal to T C over J, where T is the torque, C is the radius, and J is the shape factor. So for segment AB we have this angle, for segment BC we have this angle. Obviously now you can observe that tau max for segment BC is higher than tau max at AB. You can see that, and this is our final answer about the tau max. So in the start I have already said it is not essential that if a shaft of higher diameter it will have the higher shear stress. No, it depends upon the lot of many factors. In order to find the B part, the twisting angle at B with respect to A, we have to understand the twisting concept. In this diagram, it is shown that the point B is moved to B dash, and with respect to center, the theta AB. So in this diagram, you can have an understanding from the side view. So this is a side view. You can see that theta AB is due to the movement of B to B dash. And what the point D to D dash is indicating, basically D to D dash, the DD dash basically indicating the other part of the shaft, which is 4" in diameter. For the time being we will not consider the DD dash, we will focus over the movement of BB dash. So we know that theta is equal to TL over JGT. We have already calculated that in segment AB, T is 15 foot K, L, the length of the sector is 9 feet or 9 into 12 inches. J is the shape factor, and we know that at this point radius is 3 inch because the diameter is 6 inch, and G of steel is given. So if we calculate this, the theta AB will be 12.73 radian. C point is very important because C is not directly connected with A. There is a B at intermediate point. So our target is that to find C with respect to A. For this we have to understand this diagram, in which we show that AB is undergoes to some resultant torque of 15 foot K, and the point B move to B dash. For this we have an assumption that B and C is rigidly connected with point A and B. So when B move to B dash, D move to D dash, which means that C point will also move to C dash. And when the 5 foot K torque is applied, which is on BC segment in opposite direction, it moves the C dash point to C double dash point. This is the diagram we have already discussed between AB segment. Here D dash move showing the movement of points in BC segment at B. This is another view of that diagram. Now you can see that theta AB, which is we have already calculated, and the movement of C with respect to B due to 15 feet torque is theta BC, and no sorry, and movement of C dash point back due to 5 foot K torque to C double dash is theta BC. So the difference between theta AB and theta BC is theta AC. This can be understood by this diagram. Initially the point was at C. This is at C point in BC segment. So when 15 foot K load applied on AB segment, it moved at C point to C dash. This is theta AB. So what happened when another torque of 5 foot K applied over BC segment, it moved the C dash point to another point C double dash. This angle is called theta BC. The difference between these two angles is theta AB, and we can calculate this by this approach. We can calculate theta BC, and we can calculate theta AC by this formula. It is left blank for your assignment. After having discussion about torsional formula, the main objective of torque transfer is to transfer the power. For that, the formula is given here as P is equal to 2 pi nt. The units have already mentioned. For your assignment, find 1 horsepower is equal to how much watt, and also another assignment which you have to return in field form, that if they are not in SI unit, FPS unit, then what would be the shape of this formula P is equal to 2 pi nt. This is the question. You can read the statement yourself. I have already discussed about the shaft design while we are proving the torsional formula, that there are two ways to find the torque transferability or the size of the shaft. One is on the basis of angle of twist and material property modulus of rigidity, and other option is to find on the basis of maximum shear stress. So the given data is shown to you, and we have to find the radius of the shaft. We know the shear torsional formula, and we know this. It can be break up into two formulas. One is shear stress base and other is angle of twist base. So for both we need torque, and torque we can find from the power. Now we'll go for option 1, shear stress base. We know that it is a circular shaft. We have to find the radius. So we place the value of J in the formula, and we simplified the formula and find radius as 34.4 millimeter. So in option 2, we will use the formula of angle of twist. We will place the value of J in that formula. We can simplify the formula in terms of R. We place the known values, and we have another value of R. Now it is your assignment to verify which radius will be used, because we have two values. We have some justification. So in the assignment you will submit, you have to mention which radius is used. The hint for that assignment is given to you. You can use it and solve it. The last topic is about the relationship between solid and hollow shaft. These are some introductions. I'm just giving the final relationship. I will not go into the detail how we can prove it. And this is the description of n, where n is equal to r1 over r2. R1 is the outer radius of hollow shaft and r2 is the inner radius of hollow shaft. There is a discussion that normally the value of n is not taken higher than 2, because if we take the value of n is equal to 2, the answer will be 1.44 T solid. It means hollow shaft of same weight, same material will be 44% efficient than the solid shaft. Obviously, if we increase the value of n from higher than 2, we will increase the efficiency, but there are a lot of many problems. I think you to think yourself in assignment why it is not taken more than that. And the other assignment is that the size, when I'm talking about the size, it means the diameter of a hollow shaft and solid shaft of same weight, same material will be same or not. And this is another question given to you for to solve. So one number assignment will be given to you for following all these approach. The example, there is only two example we have discussed. You have to solve this example by yourself. You have to solve the formula. It is very important formula. I can ask you people in the paper to prove the formula, and I can give you some starting point. Like I will say that this is the discussion and this is the resisting torque formula, resisting torque. Prove this. So maybe the whole proof I can ask, maybe the segment of the proof I can ask. So you should be very clear about that proof. This is all about your this. And last important thing is that it take me almost 3 days to prepare this PPT, and my active hour over this presentation are more than 6 hours. And for you people, maybe it will take 45 minutes to read or go through that slides. If you sincerely did not give 45 minutes to this slide, how you will understand? This is the best I can do for you. Thank you very much.